Starting class here. Howdy guys, welcome back to Calc 2. I hope you're all excited as I am today to learn about more comparison tests. Particularly there's this thing called the limit comparison test that we're going to discuss today. So without further ado, let me turn on my document camera and we can get moving. All right. So this is MAC2312, section 004. It is a lecture, and today is the 23rd of March, 2021. Do take a look at the Discord if you haven't in a while. There were some questions asked there about the structure of the course moving forwards, what sections we'd be covering and when we can expect exams 2 and 3 to take place, and what sort of content will be on those tests. So if you're a little bit nervous about that, I fully recommend looking at the responses I posted on the Discord. The link to that, of course, is still in the announcements in Canvas. You can get there in case you've lost the invite link. It is still there. Today, we're going to continue moving ahead with chapter 11. We're going to finish section 11.4 by talking about the limit comparison test. So 11.4 is just on comparison tests, and there's 2 of them. The direct comparison test we learned last week. The limit comparison test I've split into this week because they're very different animals. And we want to move at a reasonable pace, but also not overwhelm. If we get through the limit comparison test in its entirety, I may introduce our second topic for this week, which is 11.5 on what's called the alternating series test. So those are the 2 topics for this week, and on Thursday we'll certainly finish 11.5, regardless of whether we started today or not. So these are the two things that we're going to be doing this week. I did just hear something happen in the Discord. I'll make sure I'm not missing anything. Oh, okay. That's all. Yeah, I'm just okay, cool. So recall. Last week we learned about the direct comparison test. And this says if 0 is less than or equal to an is less than or equal to bn, then if the sum, and it could start at 1 or 0 or infinite, any finite number down here. If the sum of the smaller guys diverges, then the sum of the larger guys diverges. And if the sum of the larger guys converges, then the sum of the smaller guys must also converge. The labels here don't matter, right? And I want to make that extra clear. Who is AN and who is BN doesn't matter. You can swap the ANs and BNs as long as you swap them here as well, and everything will still be true. The idea is if your guys are smaller than somebody else, and the big guy converges, the sum of the big guys converge, then the sum of the small guys must converge as well. And if the sum of the smaller guys diverges, then the sum of the bigger guys must diverge as well. So which role your terms play in this inequality depends on whether you think your series is convergent or divergent. If you think your series is convergent, then you will try to treat it as the ANs here and squeeze it underneath an obviously convergent series. And if you think that your series is divergent, you will try to squeeze an obviously divergent series underneath him. The theorem for today is sort of the tool you use if no such inequality exists. For example, if you know your series, or you strongly suspect your series to converge, but you cannot find a bigger series that is easy to compare against, that is to say you cannot come up with an inequality like this for the obviously related series, then you will use the limit comparison test instead. So the kind of classic example here, I'll do a DCT example first. Sigma n from 1 to infinity, 1 over 2 to the n plus 1 like this, can be shown to converge by a direct comparison with sigma n from 1 to infinity, 1 over 2 to the n. Because 1 over 2 to the n plus 1, on the one hand, is certainly greater than or equal to 0. Exponentials like 2 to the n are always positive. So you add 1 to a positive thing, you definitely get a positive thing. The reciprocal of a positive thing is positive. And this is definitely smaller than 1 over 2 to the n, because its denominator is 1 larger, right? Bigger denominator means you're smaller overall. And we know that sigma n from 1 to infinity, 1 over 2 to the n, is the same as sigma n from 1 to infinity, 1/2 to the n, which is a convergent geometric series with the absolute value of r there being the absolute value of 1/2, which is 1/2, which is less than 1. Therefore, sigma n from 1 to infinity, 1 over 2 to the n plus 1 converges by the inequality here, which I'll call star, and DCT, direct comparison test. The question I would like to pose to you, so this should be familiar, right? This is an example we ran through in detail last week. The question I would like to pose to you is, what happens if I change this plus right here to a minus? If I change this plus to a minus, then 1 over 2 to the n minus 1 is not smaller than 1 over 2 to the n. It's actually a little bit bigger because the denominator would be smaller. So an inequality like this wouldn't work. And that's what I mean by saying the kind of direct comparison with the obviously related series is not easy here, because the inequality doesn't work. So what about So what if I wanted to investigate the convergence of the series S equals sigma n from 1 to infinity, 1 over 2 to the n minus 1. Of course, that minus 1 is not a part of the exponent here. It's out of the exponent. So this is like, the first term here would be 1 over 1. And then the second term here would be 1 over 3. And then the next term here would be 1 over 7. And so on like this. The terms of this series are slightly larger than the terms of 1 over 2 to the n. Here, 1 over 2 to the n minus 1 is larger than 1 over 2 to the n. So the inequality points the wrong way. Right? Like this series is very, very similar to sigma 1 over 2 to the n. The only difference is there's a minus 1 in the bottom. And since I know sigma 1 over 2 to the n is a convergent series, I am inclined to believe that this should be a convergent series because the terms only differ by 1. However, I can't do a direct comparison. The inequality here would look like 0 is less than 1 over 2 to the n is less than 1 over 2 to the n minus 1. And being larger, being term for term, larger than a convergent series doesn't guarantee anything, doesn't tell us anything. Right? If you are term for term smaller than a convergent series, you must converge. That's what DCT says. If each of your terms is smaller than each of the terms in a convergent series, then your series is convergent. But if each of your terms is larger than the terms of a convergent series, that doesn't mean anything. It could be much larger, in which case you might diverge, or it could be just a teeny, weeny little bit larger, in which case your series might also converge. It could go either way, right? If you fit in a finite box, then you must be finite. But if a finite box fits inside you, that's no guarantee that you're finite. You could also be infinite. This is the issue that the limit comparison test aims to address. Here, I know that this guy should converge, right? I know that this series should be a convergent series because each one of its terms is really fucking close to the sigma 1 over 2 to the n series, and that is a convergent series. But the question is, how do I make quantitative that statement? How do I say this series is so similar to sigma 1 over 2 to the n that by that similarity, it must converge? And the answer is LCT. So we're going to come back to this. For these issues, we have theorem. This is our next convergence test for infinite series. In addition to going in the regular spot in your notes, this should also go into your page of convergence tests. Right after the direct comparison test is the limit comparison test. And what this says is if sigma an and sigma bn are series with positive terms and I'll call the number c as the limit as n goes to infinity, an over bn is positive, and by that I mean strictly greater than 0 and finite, then positive and finite, then sigma an and sigma bn converge or diverge together, meaning they do the same thing. Either both converge or both diverge. So this is a way of saying two series are very similar. If the limit as n goes to infinity of an over bn is positive and finite, then the series sigma an is very similar to the series sigma bn, so much so that they do the same thing. If one of them converges, so does the other. If one of them diverges, so does the other. So to use this theorem, you'll be given a series and you'll be asked, does this series converge or diverge? You need to dream up a very similar series whose convergence is easy to figure out, and then hope that they're similar enough that this number comes out positive and finite. If this number does come out positive and finite, then by limit comparison test, the two series do the same thing. And you can then go on to say, okay, since sigma bn converges, my series converges. Or since sigma an diverges, my series diverges. So you need to pick the bn's so that two things are true. The series sigma bn is very similar to the series sigma an in this sense. And the convergence of sigma bn is easy to determine. So usually your bn's here will be either geometric or p-series stuff, because those are two families of infinite series about which we know everything. So let's return to the example we were just looking at, sigma 1 over 2 to the n minus 1. I'll hold here just for a second in case anybody needs to write. Are there any questions about the statement of the theorem?
I just wanted to clarify something. Yeah.
Yeah.
So the terms of an and bn all have to be positive. Yeah.
Yes.
And then the limit as n approaches infinity of an over bn has to be positive and finite.
Correct.
Okay. Just wanted to make sure.
Yeah, that's the idea. Hamlet, be a good boy. Any other questions about the statement of the theorem?
If they converge, we're not saying that they will converge on the same value, correct?
Yeah, they don't necessarily have the same value. No, they just do the same thing with respect to convergence. They either are both finite or are both infinite. Was there another question there?
Yeah, so does an and bn, do they have to always be positive or just like at the tail, like we were talking about in the last theorem?
Yeah, this is a good thing, right? So it's true that just the tail, right? You can relax series with positive terms to series with eventually positive terms. That's true. This is a case where we can relax that hypothesis a little bit, although it won't be especially relevant. Most of the time, our series will either have strictly positive terms or will have like every other term negative. Okay, so let's see how to implement this. So same thing, investigate the convergence of S equals sigma n from 1 to infinity, 1 over 2 to the n minus 1. Hamlet, no, Bubba. No. Stop this. I love you. Stop this. I'm going to run the limit comparison test. The first step in running the limit comparison test is to pick Bn. Sorry, let's see what's happened.
Thank you.
So our first step here is to pick Bn, I want it to be really similar to this, meaning having the same asymptotic behavior, like growing or decaying at the same speed, but be simple enough that I can say right away whether the series sigma Bn converges or diverges. And we know what this thing is super similar to. This thing is super similar to 1 over 2 to the n. So first you pick Bn. Second, you calculate C as the limit as n goes to infinity of an over Bn, which in this case will be the limit as n goes to infinity of 1 over 2 to the n minus 1 divided by 1 over 2 to the n. And now we have to actually crunch out the limit. There's a little bit of work here. This is lim n to infinity. If you flip and multiply, you get 2 to the n over 2 to the n minus 1. At a glance, this looks like infinity over infinity. So you could apply L'Hopital's rule. The derivative of 2 to the n is 2 to the n times the natural log of 2. So we have that upstairs, and then downstairs you have 2 to the n times the natural log of 2 minus 0. Because the derivative of 1 is 0. So of course this is just 2 to the n ln2 over 2 to the n ln2. And you can cancel. Everything cancels. And you just get lim n to infinity of 1, which is 1. Allocate. No, baby. These animals. I'm sorry, guys. So the limit of the an over bn, the number we call c, in this case comes out to 1. Since c equals 1 is positive and finite by the limit comparison test, the two series sigma n equals 1 to infinity 1 over 2 to the n minus 1 and sigma n from 1 to infinity 1 over 2 to the n converge or diverge together. That's what the limit comparison test says. Notice that I have not yet shown that my series is convergent or divergent. All the limit comparison test does, and you must remember this, all the limit comparison test does is tell you if two series play the same. So I know that this series and this series do the same thing. I don't yet know whether this series converges. In order to finish the problem, I will go on to say what this series does. And then I can deduce that this series does the same by the work we just did here. So your next step is to say something like, moreover, sigma n from 1 to infinity 1 over 2 to the n is a geometric series with the absolute value of r equal to 1/2, which is less than 1. So sigma n equals 1 to infinity 1 over 2 to the n converges. Hence, by the work above, our series S equals sigma n from 1 to infinity 1 over 2 to the n minus 1 converges also. So this is what that solution looks like. And without that third step, you're not done. You can show that two series do the same thing, but unless you know what the second series does, you don't learn anything about the first series. There was a question about this derivative here. This is a differentiation formula from Calc 1 that we should remember. d dx of a non-natural exponential b to the x. This is b to the x times the natural log of b. Any other questions about this solution?
I have a question.
Yeah.
Right. So as you were solving this, where did you get the Riemann sum of 1 over 2n? In a test, would you provide us with the second one, or we're supposed to know a similar one from the first one so we can compare them?
So just to be clear, no Riemann sums here. These aren't Riemann sums. These are just infinite series. I chose Bn to be 1 over 2 to the n. And I chose that based on the kind of essential behavior or asymptotic behavior of this guy. So you will have to pick your Bn. That's your first step, is to figure out what you're going to compare with. The reason I think this series converges right at the start is because I realized that it's very, very similar to 1 over 2 to the n. The only difference between this guy and this guy is the minus 1 here, right? So if I'm asking what does this series do, my brain goes, oh, well, this is so similar to 1 over 2 to the n that I think it should converge because I know that 1 over 2 to the n converges. So it's up to you to do this first step, to figure out what you're going to compare against. And the trick is to look for the dominant term in the top and the dominant term in the bottom. So I'll show you some more examples, but yeah, it is going to be up to you to decide what series you're comparing against. And the way you choose what to compare against is you look at the terms of your series and you ask, what's the dominant term upstairs and what's the dominant term downstairs? What are like the important pieces of this? What are the fastest growing pieces in the top? What are the fastest growing pieces in the bottom? Upstairs here, I just had a 1. So, okay, well, it's not fast growing, but that means the dominant term upstairs is 1. Downstairs, I have a 2 to the n and also a minus 1. 2 to the n grows really, really, really fast. This minus 1 doesn't do shit. So the dominant term downstairs is 2 to the n. So I chose the thing to compare against by taking the dominant term of the top, which is 1, and the dominant term of the bottom, which is 2 to the n. So I say, I think this thing is very, very similar to sigma 1 over 2 to the n, because the only difference between the two is the minus 1 here.
Okay. So as long as you pick the most important terms, that can be your Bn?
That's the idea. Yep. Now, there are exceptions to this. Sometimes it's hard to see what the dominant term is. Sometimes some things, not everything is a nice, neat fraction with a fast-growing thing downstairs and a non-fast-growing thing upstairs. Sometimes this is a little harder. And I'll show you some kind of tricky examples. But yeah, that's the general idea. All right, let's try one more. Nala. Hey, kitty. Sorry, guys. My animals are all on crack today. Let's say Let's say we're looking at something like this. The top and bottom here are both polynomials. And so our initial instinct should be to look at the dominant terms upstairs and downstairs. We might try a direct comparison, but it's not immediately obvious which way the inequality would point. Right? If we wanted to direct compare against 2n cubed over 4n to the 4, I would need some idea of whether this converges or diverges, and I would need to build an inequality pointing in the direction that would help with that. Since the dominant term upstairs is degree 3 and the dominant term downstairs is degree 4, I get the feeling that this thing is kind of like 1 over n, which means it should diverge. But I don't know that. I don't know that for sure. That's just the gut feeling we get based on the degrees of the top and the bottom. If I wanted to show that this diverges by using a direct comparison with 1 over n, I would need to then show that these terms are all bigger than 1 over n, but they're not. They're not, because the bottom is actually smaller. That's this minus n cubed fucking things up. That makes this guy bigger. But up here, I've also got this minus 3n fucking things up. And the inequality, it's not in any way obvious that it'll point in the direction you want it to. So this is a good example of a case where a limit comparison can be really helpful. So as always, we tell our reader what we're doing. We say, I'm going to run the limit comparison test. And our first step is to pick Bn. Now, what I said a second ago, the dominant term upstairs is the n cubed. The dominant term downstairs is the n to the 4. I don't care about the coefficients. Upstairs n cubed, downstairs n to the 4. So I'm going to pick Bn to be n cubed over n to the 4, which is just 1 over n. This is nice because I know sigma 1 over n diverges. I'll be able to wrap up things at the end very cleanly using an argument involving p series. But before I can do that, I need to calculate c, which is the limit as n goes to infinity of an over bn, which here is going to look a little bit messy, but we can do it. There's nothing too hard about this. This is the limit as n goes to infinity of, upstairs I'll have a fraction, downstairs I'll have a fraction. Upstairs here I have 2n cubed minus 3n plus 1 all over 4n to the 4 minus n cubed. That's my an. Downstairs, I just have bn, which is 1 over n. And to calculate this limit, I will flip and multiply the 1 over n. That'll give me, I'll write it out, 2n cubed minus 3n plus 1 all over 4n to the 4 minus n cubed times n over 1. And of course, we know we need to treat these like they're in parentheses. So we'll distribute the n. If there's something else here, we would distribute that too. It's just a 1. This is going to give me 2n to the 4 minus 3n squared plus n divided by 4n to the 4 minus n cubed. And there's a bunch of ways to take this limit. You can use L'Hopital's rule if you want, but it's going to take 4 applications of L'Hopital's rule. I don't want to do that. You can use the renormalization trick, where you divide top and bottom every term by n to the 4. Let's do that. That would give me 2 minus 3 times 1 over n squared plus 1 over n cubed, all divided by 4 minus 1 over n. And now you see that this term is going to 0 as n goes to infinity. This term is going to 0 as n goes to infinity. And this term is going to 0 as n goes to infinity. So you get 2/4, or 1/2 for C. Now, as in the previous problem, we can say since C equals 1/2 is positive and finite, sigma n from 1 to infinity 2n cubed minus 3n plus 1 over 4 n to the 4 minus n cubed converges or diverges together with sigma n from 1 to infinity 1 over n. That's the end of the comparison. Now to finish things up, we say something like, moreover, since sigma n from 1 to infinity 1 over n is a divergent P series, here P is equal to 1, which is not strictly greater than 1, we learn that our series, sigma n equals 1 to infinity, 2n cubed minus 3n plus 1 over 4n to the 4 minus n cubed must also diverge. So that is how these go. It's a meaningful amount of work, and most of the work is in the writing. The limit here is not terribly hard to come up with, but there's a creative step at the start where you have to choose your BNs. This creative step can be challenging, and I'm going to show you in my next two examples some cases where these can be harder to figure out. But the majority of problems like this will be just like the two we've seen. Very, very simple to pick BN. Just take the strongest term upstairs and the strongest term downstairs, form a simple ratio out of those, and that will be your BNs. Calculating the limits here, your limit skills need to be good. We've been saying this since 11.1. This is not the last place we're going to need limit skills like these. We're going to see these in the root test and in the ratio test as well. You're going to see these in the alternating series test. All through chapter 11, these limit skills are crucial, so you need to be good with this stuff. But then the majority of the work is actually over here. It's just in applying the logic correctly. So I'll give you a second to get this copied down while I refresh my coffee and think about any questions you may like to ask. Questions on this?
Would it have mattered if we interchanged AN and BN here?
Well, AN and BN, the theorem is symmetric in AN and BN. That is true. The theorem does not care which one you call AN and which one you call BN. However, there are some special cases, some slightly deeper cases of this theorem which are asymmetric in AN and BN. So this is something that I was going to hold on to until a little bit later, but since you're asking, I'll go ahead and say, let me show you this problem in the textbook. This would be a good way for you to answer this for yourself with just a little bit of a hint from me. If we dig deep into the 11.4 exercises, deeper. Oh, yeah, I'm getting there. Here we go, 41. So if sigma AN and sigma BN are series of positive terms, and sigma BN is divergent, prove that if the limit of the AN over the BN is infinity, then sigma AN is also divergent. Note, this doesn't say that they do the same thing necessarily. If the limit of the AN over the BN were infinity and sigma BN were convergent, we wouldn't learn shit. But if the AN over the BN goes to infinity and sigma BN is divergent, then you can conclude that sigma AN is also divergent. You have to think about what this would mean. If the limit of the AN over the BN is large, that means the ANs are all bigger than the BNs. So this would really say that AN is substantially larger than BN. That's what this limit would tell us. So if the sigma BN is divergent and the ANs are substantially larger than the BNs, then sigma AN is also divergent. Similarly, if you look back here at question 40, there's another way to make this asymmetric. If sigma AN and sigma BN are both series of positive terms and sigma BN is convergent, then if the limit AN over BN is 0, then sigma AN is also convergent. The limit AN over BN equaling 0 means the BNs are substantially larger than the ANs, right? If a fraction is going to 0, is close to 0, that means the bottom is bigger than the top by a lot. So here that would mean the BNs are a lot bigger than the ANs. So if sigma BN is convergent, then sigma AN would also be convergent. So there are two asymmetrical versions of this theorem, but they are not, they're sort of, enhancements on the theorem. The regular theorem is symmetric in AN and BN, but these sort of enhanced versions are not symmetric in AN and BN. So I encourage you with the limit comparison test to always think of your series as sigma AN and you pick the BNs. Because there are these other versions and these labels are the standard labels, that would be my advice. But if you prefer to just worry about the symmetric version, if you are not required to solve exercises 40 and 41, they're not going to be in your homework. If you prefer to think just about the theorem as stated to the class, then yes, the theorem is symmetric in AN and BN. So you could interchange AN and BN outside of these cases. But it's not terribly uncommon to like pick your BN and then be like, oh shit, the limit is 0. What do I do? 0 is not positive. And in that case, it's nice to have this extension. Or, over here, it's possible that you pick your BN, calculate C, it comes out to infinity. That's not finite. Can I still do anything? Yeah, as long as these other requirements are met. But it's up to you whether you want to explore those. I invite you to explore those. These right here are some of the best exercises in the whole textbook.
When you're picking your BN, are you considering the limit, or are you only picking something that's similar to the AN?
Yes. I am picking something that is similar to the AN in the sense that I expect the limit to be positive and finite. So the way I'm determining similarity, the tricks I've given you so far are precisely the tricks that you need to guarantee that the limit comes out finite. So yes, to both. Kind of the way we're choosing similarity is by thinking about that limit. But if it helps you to just think about similarity in the terms I described, and I think for most people it does, then I would encourage you to do that because it does the other at the same time.
So when you say like the way you describe it, you just mean like you took I forget how you ordered it, like the leading terms or the leading.
Yeah, the dominant or fastest growing term.
Yeah, that's how you ordered it.
Fastest growing term of the bottom. Yep. Because it's those, so there's this whole field of mathematics called asymptotics, right? Like what happens as the inputs get large, those are called asymptotics in the same way we talk about asymptotes. And when we're saying take the dominant term upstairs and the dominant term downstairs, what we're really doing there is identifying the asymptotic behavior of that function. Let me show you an example what I mean and see if we can connect it to asymptotes. Unfortunately, here at Santa Fe, we don't do a whole lot of work with what are called oblique asymptotes or slant asymptotes. But if I take, for example, the function f of x equals x plus 1, let's do, how about x cubed plus 1 over x minus 1. X squared plus 1 is fine. So if you look at this graph, you'll notice that there is some interesting behavior as you walk far and far, far and far away from 0. If I wanted to know what that interesting behavior is like, I take the lead term of the top over the lead term of the bottom. That would just be x. I may have to shift it up or down to make it match. But look at this. So as you go further and further and further from the origin, x squared plus 1 over x minus 1 looks more and more and more like y equals x plus 1. The plus 1 here doesn't matter. The idea is that this function, the red function, is growing at the speed of x as you wander further and further and further from the origin.
So you're just looking at end behavior, really.
Right. That's precisely it. End behavior is what we're looking for. When we're picking the Bn, we're trying to pick the Bn to have the same end behavior as the Ans. And the way you do that is by looking for the dominant or fastest growing term in the top and the dominant or fastest growing term in the bottom. What this means, when you say that the limit of the An over the Bns is finite, you're saying that An and Bn have the same end behavior. That's precisely what that means. And if An and Bn have the same end behavior, then their series have very similar tails. So if the tail of the one series is finite, then the tail of the other series is finite. And that's precisely what it means to converge for a series. So these things all connect to each other through some very beautiful logic, and you're going to need to spend time thinking about it and asking yourself questions like those Alexander is asking now in order to wrap your head all the way around this. It's good stuff, but it requires some thought. Any other questions on this example? It's a really nice discussion. I'm grateful for your questions. So if you have others, please ask them.
I assume you also want to pick Bn such that you can find out whether it's convergent or divergent easily as well.
Right. So that's the kind of dual challenge here, is picking the Bn to have the same asymptotic behavior as your An, but also picking the Bn so that it's easy to tell whether sigma An converges or diverges. Most of the time, your Bn's will be like a p-series thing or a geometric series thing. Most series can be compared to one of those. I'm going to give you now a slightly harder example. I've got two kind of challenging examples for you today. This is sigma n from 1 to infinity sine of 1 over n squared. I know, I know. Here's the hint. this is one of your special trig limits from Calc 1. This is a limit that we usually prove using geometry tools back in Calc 1, a geometric argument, and we need it to show that the derivative of sine is cosine. That's where this shows up for the first time, is as you're getting your first few results on derivatives, you want to show that the derivative of sine is cosine, and in that process, you bump into this limit, usually written with h's instead of thetas, but whatever, and you show that this limit is 1. What this means is, for very small theta, sine theta over theta is approximately equal to 1. And that's equivalent to saying that for very small theta, sine theta is approximately equal to theta. I'm sad to hear that limits regarding trig were not covered well in your Calc 1 classes. We now have the benefit of L'Hopital's rule, right? You can prove this limit is true using L'Hopital's rule also. It's that the first time you see it, it's addressed using a geometric argument because that shows up before you know how to differentiate. So you can't use L'Hopital's rule to prove this the first time. You have to use a geometric argument because you don't know what derivatives are and therefore can't use L'Hopital's rule. But with hindsight, we can use L'Hopital's rule to get this. You know, the top and bottom both go to 0. The derivative of the top is cos theta. The derivative of the bottom is 1, and cos of 0 is 1. So the fact that this limit is 1, even if you haven't seen it before, you can verify it. You can verify it quite readily using tools that by now we should be comfy with, even if you didn't get a good treatment of it back then. I would be happy to show you why this limit is 1. That could be something that we talk about in lab this week if you guys like. The geometric argument, and there are several, are not that bad. They're usually using the squeeze theorem and based on inclusion. You look at the unit circle and draw a couple triangles and make a geometric argument. But the upshot is, if the inside of sine theta is small, then sine of that angle is approximately just that angle.
Can I make a guess on where we're going to go from here?
Please.
Are we going to choose Bn to be like 1 over n squared?
Yes, sir. Care to explain why?
Because we want to make it look like the limit as theta approaches 0 of sine 0 or sine theta over theta. And so if we have sine of 1 over a really big number, that's going to be sine of 0. Then if we have that over 1 over a very big number, that's going to be 0 over 0, just like that.
Perfect. Yeah, that's wonderful. That's exactly correct. So if n is large, then 1 over n squared is close to 0. So for large values of n, sine of 1 over n squared, imagine theta here is 1 over n squared. For very, very large values of n, sine of 1 over n squared should be approximately equal to 1 over n squared. In other words, our first step here will be to pick Bn exactly as Alexander said as 1 over n squared.
I have a concern here.
Yeah.
1 over n squared is going to converge, yeah?
Sigma 1 over n squared is a convergent piece.
That's what I meant.
Yep.
Why is that not this? Well, why can't we then just choose 1 over n, which wouldn't?
Well, if so, let's take a look. If you chose Bn to be 1 over n, then the limit would not come out to be positive and finite. That's the case. So we'll take a look at this limit and I'll be able to give you an argument. It's not just sine 0 over 0. It's that the inside of sine needs to go to 0 at the same speed as the thing downstairs. So sine 0 over 0 is undefined. It's not necessarily 1. It's that the object inside the sine theta here is going to 0 at the same speed as the object downstairs. So if this was sine of 1 over n squared divided by 1 over n, that limit would not be 1. The inside of sine theta needs to match the thing downstairs exactly.
So coefficients wouldn't matter here. It's just about the powers.
Right, yeah, it's true that the coefficients don't matter. And in general, constant multiples have no effect on convergence of infinite series or integrals or sequences. But the powers matter. The speed at which the objects are growing or decaying is what matters, not so much the size of the objects, it's the speed, their rates of change. So we've chosen our BNs, and now we calculate C as the limit as n goes to infinity of an over bn, which in this instance will be limit n to infinity sine of 1 over n squared divided by 1 over n squared. And you cannot cancel the 1 over n squared, right? This upstairs here, this is not multiplication. This is function composition. This is the sine of 1 over n squared.
Do you see that mistake?
I do, yeah. I've seen, while we're here, as a little bit of math teacher humor, I've seen things as absurd as, some space. I've seen things like sine x over x, cancel equals sine. Shit like that is not at all uncommon. There are funny versions of this stuff too. I won't, sine x over n, believe it or not. Seen this. It gets worse. But
Do you see this in Cub 2 classes?
from time to time.
That's horrifying. I'm so sorry.
That's all right. This is just life. But from here, we need the appropriate tool to calculate the limit. And if cancellation of the 1 over n squareds is not the appropriate tool, what is? So 1 over n squared goes to 0, right? So this looks like sine 0 over 0. The sine of 0 is 0. So this looks like 0 over 0. So what would be the appropriate tool to carry on from this step?
L'Hopital's.
Good, L'Hopital's rule. Yeah, so Josh is correct in saying we should use L'Hopital's rule here. This is an indeterminate ratio. These certainly are differentiable functions. So the natural thing is to apply L'Hopital's rule. The derivative of the bottom, if you differentiate 1 over n squared, I would recommend doing it as a power function. That's n to the minus 2. The derivative would be -2 times n to the -3, or -2 over n cubed. And upstairs, we need the chain rule. So the derivative of sine of 1 over n squared is cos of 1 over n squared times the derivative of 1 over n squared, which we just said is -2 over n cubed. And the sort of magic here is that thanks to the chain rule, we get a factor of -2 over n cubed that can be canceled top to bottom. Now, having done that, I just look at what my limit is now. We've done one run of L'Hopital's rule. I now have cos of 1 over n squared all over 1. All right, because when you
Which is cos of 0, which is 1, which is positive.
good. Yeah, this is cosine of 0, which is 1. So since c equals 1 is positive and finite, sigma n from 1 to infinity sine 1 over n squared converges or diverges together with sigma n from 1 to infinity 1 over n squared. I should have put a 3 here. I'm sorry, that's our third step. It's just to summarize what LCT says. And then our final step is to say, we know sigma n from 1 to infinity, 1 over n squared is a convergent p-series. Here p is equal to 2, which is bigger than 1. So by the limit comparison test, sigma n from 1 to infinity sine of 1 over n squared must also converge. So this is the gain.
In our first step, if we had written bn equals 1 over n squared and an equals sine of 1 over n squared, could we then just, instead of writing out the entire function again and again, could we just write like sigma an, sigma bn?
I'm okay with that, but you got to keep things clear. Make sure you don't swap them up and make a mistake. So you see me, I try to avoid pronouns. When a pronoun will suffice, just use the noun instead. That's the general kind of ethos here, because it makes it less confusing for your reader. Like the word it, you'll never see me write it converges. All right, it's always this particular series converges, or at worst, the series S converges. That sort of habit is a good habit to get into, because shorthand, especially when there are multiple objects being referred to, can be very confusing. So I'll say, if you want to say sigma an converges instead of writing it all out, I'm fine with that, but please don't say it converges, because I don't know what the it is you're referring to. Could mean sigma an, could mean sigma bn, could mean some sequence. Who the fuck knows? But yeah, if you want to write sigma an here and sigma bn here, sigma bn here and sigma an here, I would be okay with that. I don't have a problem with it. Just make sure you keep it straight, because if there's an error there, then I would have to be a little bit ruthless in grading, because it, of course, would not be a true statement. So if you're going to use a shorthand to refer back to these things, just make sure that you use it correctly, and please avoid pronouns. Just use the actual noun or a symbol representative of a particular noun rather than the word like it.
Is it possible when we do that limit, is it possible for it to be 0? And what would that mean?
So if the limit here comes out to 0, the test is inconclusive. If the limit comes out to 0, or if the limit comes out to infinity, then the test is inconclusive and you need to go try a different choice of bn.
Or if it's negative, yeah.
Yeah, well, so the good news is, since you can only apply this to terms with positive an and positive bn, you'll never get a negative number out. A ratio of positive things is at worst going to be 0. You'll never cross over 0 to the other side. So the whole test only works for series with positive terms. And that's an important observation. If the series has any negative terms, can't do this. Again, there are ways to relax these hypotheses, but this is the starting point. Is that to apply either of the comparison tests, we should be talking about series with positive terms. And then if you get a non useful result out of this limit, then you need to start back over and try something else for bn. There was the question earlier, what if we'd chosen bn to be 1 over n instead of 1 over n squared? In that case, this limit would have come out to 0. And we would go, oh shit, I need to start over with a different choice of bn. If I'd chosen bn to be 1 over n cubed or something like that, then the limit would have come out to infinity. And again, I'd have to come over and choose a different bn. All right, how are we?
Because then you wouldn't have the -2 over n cubed canceling like it does here.
Correct, yeah. Yeah, your derivative down here, for example, if you'd chosen 1 over n cubed, this would be like a -3 over n to the 4. You could cancel the n cubes, but then there'd still be a copy of 1 over n downstairs. He would flip upstairs and blow the whole thing to infinity. How are we feeling about this? We feeling pretty good? All right, fun fact. What works for sine works for tangent. So if you see tangent of 1 over n squared or tangent of 1 over n, the same shit works, because if you replace sine with tangent here, same thing works. Tan theta over theta goes to 1 as theta goes to 0 as well. So a little note, if you swap this sine for a tangent, you can swap all the sines for a tangent. Everything else works fine. Your derivative, of course, would be a secant squared, 1 over n squared here, instead of a cosine, but it all goes just fine. So what works for sine in this sense works for tangent as well. I do have one other interesting example of limit comparison problems for you guys. This is a weird one. So the objects being summed are the nth root of 2 minus 1. Just for shits and giggles, the first few terms of this series are 2 minus 1 plus the square root of 2 minus 1 plus the cube root of 2 minus 1 plus, and so on.
Professor, I have a quick question.
Yeah.
So how come sometimes when you're writing the series, sometimes you write the S equals, and sometimes you just start with the normal Riemann sum?
Well, I'll choose to put an S out here if I intend to refer back to the series later and I don't want to write the whole thing. So there's kind of a lot to write here, and I know I'm going to have to refer back to it later. So giving it the name S gives me a way to refer to the series without writing the series explicitly. Kind of like what was asked just a second ago. Like, can you write sigma an instead of writing the whole thing out? Sure. And here is a way that you can also be lazy like that. Instead of writing this whole thing, when I refer back to it later, I can just write the letter S instead. So think of it as I'm naming the series. I can call it Joe or Bob or whatever else I want, but I'm just calling it S for series.
Sounds good.
We all come to you with what the first few terms of this series look like and what it is that this series is adding up. It would be natural to try a few other things like TFOD. You can look at the limit as n goes to infinity of the ANs, which is the limit as n goes to infinity of the nth root of 2 minus 1, which is lim n to infinity 2 to the 1 over n minus 1, because that's what the nth root is. What is this limit? What does the 1 over n go to as n goes to infinity?
0.
Good. So this is 2 to the 0 minus 1, which is 1 minus 1, which is 0. So do we learn anything? No, this is inconclusive. Remember, if the limit of the ANs is not 0, then the series diverges. If the limit of the ANs is 0, then TFOD is inconclusive. I love this example because the first time I saw this, a student brought it to me. And the first time I worked on it, I got nowhere for about 10 minutes. It ate up a meaningful portion of a lab about 3 years ago. And I remember being like, shit, I just don't see it. But then there was this beautiful click moment. And the click moment came from thinking of AN as 2 to the 1 over n minus 1. Unfortunately, the minus 1 really is important here. It's not one of those cases where you can just say, oh, the 1 doesn't matter, and so we throw it away. The -1 is what allows these to go to 0, right? Because as the 2 to the n, 2 to the 1 over n gets closer to 2 to the 0, this thing is what's dragging us closer and closer to 0. But if you think about the derivative of the ANs, this guy goes away. This guy's derivative would be 2 to the 1 over n times the natural log of 2 times the derivative of 1 over n. So I'll let you think about this for just a second before I spoil it. We're going to do this with a limit comparison. And my hint is that since an looks like this, an primed, the derivative of an has 2 to the 1 over n times the natural log of 2 times the derivative of 1 over n. All right, because 2 to the x, his derivative is 2 to the x natural log of 2. We talked about that earlier today. So by the chain rule, you would have 2 to that stuff times the natural log of 2 times the derivative of the stuff inside. So if I wanted something to cancel with this term, after applying L'Hopital's rule within the limit comparison test, I would need a 1 over n. If the thing downstairs in my limit comparison test is a 1 over n, then when we apply L'Hopital's rule, you'll have a derivative of 1 over n upstairs and a derivative of 1 over n downstairs, which can cancel, leaving just this stuff, which has a positive and finite limit. So the move here, big brain move, is to pick Bn to be 1 over n, and it is not at all obvious. So when I said there are exceptions to the dominant term upstairs, dominant term downstairs, the two problems we've looked at here are the two I have in mind. There are many others, but these are the kind of families that those fit into. Certainly here, I'm not picking a dominant term upstairs or downstairs. It's not like that. This thing isn't even a fraction. But I'm asking, what is the rate of growth like? I'm asking, what does the derivative of the an look like, to help me figure out what the rate of decay for this apparatus is. These pieces, as n gets larger and larger, tend towards a constant, like 0.6. So the derivative of an is proportional to the derivative of 1 over n, meaning an and 1 over n decay at about the same speed. So the symbol for proportional is like an elongated alpha. This is proportional to the derivative of 1 over n. And that's the hint to pick Bn as 1 over n. It's a tricky, tricky problem. This much harder than something I would put on a test, just to be clear. All right, this is above exam level, but it is a good thing to get thinking about. So we pick Bn to be 1 over n. We're running the limit comparison test, so we're going to calculate C as the limit n to infinity, an over Bn, which in this case is the limit as n goes to infinity of 2 to the 1 over n minus 1 divided by 1 over n. Both the top and bottom here go to 0. So we will run some L'Hopital's rule. The derivative of 2 to the 1 over n minus 1, I talked about that up here. That's 2 to the 1 over n times the natural log of 2 times the derivative of 1 over n, which is negative 1 over n squared, divided by the derivative of 1 over n, which is negative 1 over n squared. And we can cancel these pieces. meaning what we have left is lim n to infinity 2 to the 1 over n times the natural log of 2, which is 2 to the 0 times the natural log of 2. And 2 to the 0 is 1. So this is ln2, which is somewhere around 0.6. Later in the semester, I'll be able to give you a cool tool for approximating the natural log of 2. That'll be fun, but a totally different thing. So, since c equals natural log of 2 is positive and finite, S converges or diverges together with sigma n from 1 to infinity 1 over n, which is a divergent p-series. P there being equal to 1. Thus, S must also diverge. And this is a fun one. This is a divergent series whose divergence is exceptionally hard to detect. And I'm not aware, and I mean this not just like with tools of Calc 2, but with all of my years of experience in real and complex analysis, a total of 7 or 8 graduate classes and years of research, I'm not aware of any tool besides the limit comparison test which will show you that this series diverges. It's so close. It's so fucking on the edge. This thing is right there trying to converge really hard, but it doesn't. And LCT gets it no problem. It's very, very cool. The real challenge in all of these, assuming that your background skills are sufficient, is this, the creative step, where you have to pick your BNs. And I've done my best to give you some hints. So the dominant term upstairs, dominant term downstairs thing, that's your number one biggest, best hint for picking BN. Think about asymptotics. Think about what is the end behavior of my ANs. Barring that, there are a few of these other tricks, right? Like sine and tangent, as long as their insides are going to 0, behave a lot like their insides. So sine of 1 over n behaves a lot like 1 over n. Tangent of 1 over n cubed behaves a lot like 1 over n cubed. Besides that, if you're not landing into one of those categories, then the game is to think about the derivative of the ANs. Try to find some simpler function whose derivative is similar to the derivative of the ANs. So here the derivative of the AN has this piece which goes to 1, this piece which is a constant, and then this piece, which is what really tells me the growth rate of the ANs. So I pick BN to be that piece. I'll go ahead and pop open the homework right after class here. You guys are encouraged to get in there and take a look at those few of those problems right away. I also, again, want to encourage you to look in the textbook at the later problems. Remember, the homework that I assign in WebAssign is the absolute bare minimum. There's so much other stuff out there, and you really should look at some of them. A bunch of these are really good problems. This one, this one, this one. Lots and lots of these are excellent and just don't work well in WebAssign. So please take a look at the book. If you want harder problems to play with, all of the proof problems on the back here are excellent, excellent problems. And these will each occupy your brain for a few hours. So if you're looking for something fun to think about, any of 38 through 46 would be a good idea. If you're looking for problems that are about at the exam level, any of 3 through 32 would be good. We are out of time, so I'm not going to introduce 11.5 today. Thursday, we will go through 11.5. This is going to be a one class thing. We'll get through all the way through 11.5 on Thursday. It's not a hard section, which frees up next week to talk just about 11.6 and 11.7. Probably Wednesday of next week, I will release your study guide, which means our exam 2 will be the following Wednesday. That's about what we're looking at. If we get through
Wednesday?
11.6 on Monday, sorry, the following Wednesday. So if we get through 11.6 on Monday, I may release the study guide then, which would mean your exam 2 would be the following Monday. But either way, exam 2 is going to be week after next, either Monday or Wednesday. So just keep that in mind. Make sure you're keeping up with the homework. If there's any stuff that has kind of fallen to the wayside, please get your extension requests in so I can grant them and you can get that shit knocked out, because the most important thing is practice, right? You must practice solving problems.
What time on Monday?
Well, normal class time. Yeah,
Oh.
if you were to do it on Monday, I'm sorry, no, Monday you don't have class. I'm so sorry, Tuesday. I was thinking Monday, Wednesday, Friday class. Yeah, no. So your exam is going to be Tuesday after next. Tuesday after next during class time, most likely. But I'll talk more about that as we get closer. Like I said, early next week I'll release the study guide. It depends on how long it takes us to get through 11.6. Any questions before we go, gang? Alrighty, that's all from me. I hope you guys have a lovely afternoon. And if you do want to talk about anything, don't hesitate to send me a Canvas message or an email. Come by office hours. All of those things are good moves. Take care, guys.
Have a great day, Professor. See you later.
Thank you.